have the limit as x approaches 0 of the absolute value of x divided by x. So this is a two-sided limit. It's a normal limit. So that means we have to consider both approaching 0 from the left and approaching 0 from the right. Recall, when we're dealing with absolute value functions, we create piecewise functions. Namely, when the inside of the absolute value is positive, the function stays as is. So if x plus 3 is positive, we tend to set it equal to greater than or equal to 0. Therefore, x is greater than or equal to negative 3. You're going to have the same exact function. However, if x plus 3 is less than 0, namely when x is less than negative 3, the inside of that function is going to be negative. And when the inside of that function is negative, we deal with the opposite of said function. So this is the piecewise function. When the inside is positive, namely when x is greater than or equal to negative 3, the function we're dealing with is x plus 3. However, when x is less than negative 3, the function we're dealing with is negative x minus 3. Sorry, that's a little bit off the screen. Okay, when x plus 3 is positive, namely when x is greater than negative 3, we're going to be dealing with the same exact function. However, when the inside is negative, x is less than negative 3, then we're dealing with the opposite function. So we're going to do the same thing here. We're going to say that when x is greater than 0, we're dealing with the same exact function, which is x. When we have x over x, the limit is going to approach 1. However, when this inside is negative, and you could simply consider that x plus 0 is negative, x less than 0, we're going to be dealing with the opposite of what you see. The numerator stays as x both times because that's not involved with the absolute value, and you're going to get negative 1. Therefore, the limit as x approaches 0 from the right is this, positive 1. However, the limit as x approaches 0 from the left is negative 1. Therefore, this limit does not exist. Very quickly, this would be the graph of this function. Like so. So when x approaches 0 from the left, the y value is going to approach or stay at negative 1. As the x value approaches 0 from the right, you're going to get a y value of positive 1. Therefore, again, this limit does not exist. Next, we have the limit as x approaches 0, a normal limit, a two-sided limit of x divided by the absolute value of x plus x squared. Again, we're going to consider two situations. One, when the inside of this absolute value is positive or equal to 0. When we have that scenario, we literally are just going to remove the absolute value signs and proceed. Here, down below, we're going to pull out an x as a GCF. We're going to have 1 plus x. I always recheck, redistribute, make sure we did it correctly. We have x plus x squared. X's cancel out. When you insert 0 here, you're going to get positive 1. Next, for the situation where the inside of that absolute value is negative, that means we take the opposite of what we see. Everything else stays the same. The only thing that becomes opposite is what's inside the absolute value. Okay, so here we're going to pull out again a negative x. We're going to have 1 minus x. Let's again double check. If we redistribute, we're going to have negative x plus x squared. These x's cancel out. We get a minus 1 on the top. If you insert a 0 here, which is the same as just putting your thumb over it, you're going to get negative 1. Therefore, since you get two different limits, this one does not exist.
Next, we have the limit as x approaches 4 from the right of the absolute value of 16 minus x squared over x minus 4. Okay, if we're approaching 4 from the right, that means we're going to be dealing with numbers that are bigger than 4. That means if we perform this operation, we're going to have 16 minus a number that's bigger than 16, which means this is going to be negative inside the absolute value sign. If the contents of the absolute value sign are negative, we work with the opposite. If we distribute that negative, we're going to have negative 16 plus x squared over x minus 4, and we recognize this as x plus 4 over x minus 4 divided by x minus 4. We can now cancel these out, and now we can plug the limit directly in, and the final answer is 8. Let's do this limit approaching 0 from first the right and then the left. We have 1 over x minus 1 over the absolute value of x. Excuse me. So here, as we're approaching 0 from the right, we are dealing with positive numbers. Therefore, essentially, we're just going to erase these absolute value signs and deal with the positive version. We're going to have 1 over x minus 1 over x, and this is going to be 0. Here, as we approach 0 from the left, we're going to be dealing with negative numbers. Therefore, yes, we will take away the absolute value signs, but we will deal with the opposite of what's inside. Now this becomes a limit of 1 over x plus 1 over x. The denominators are the same. We're adding fractions. We're going to keep the denominator and add the numerators. Okay, so now we have the limit as x approaches 0 from the left of 2 divided by x. So as these numbers get very, very close to 0, x is going to become something like negative 1/millionth. We're going to do keep, change, flip, and this limit is going to head towards negative infinity. As we move on to discussing limits as x approaches infinity, we need to review what are called indeterminate forms. These are limits that are going to require further algebraic manipulation. These are limits that are going to involve conflicting behaviors that tend to cancel each other out. So for example, if you plug in infinity for x in the numerator and denominator and they're both headed towards infinity, unfortunately, you're not allowed to cancel this out and say that the limit equals 1. You need to do further manipulation or further analysis. And the ones listed here are indeterminate. Note, however, that 0 plus infinity is equal to infinity. You're allowed to say that. But let's focus on this one, for example, infinity minus infinity. You might be tempted to say, well, that's going to equal 0. But that's not true. For example, let's look at this limit as x approaches infinity of e to the x minus x. It's helpful to look at the graphs of each of these. E to the x is going to be a growth function with a horizontal asymptote at y equals 0, and growth functions move away from the horizontal asymptote like so. Therefore, as x approaches infinity, the y value is going to be infinity. So we're going to have infinity minus, and then if you have y equals x, we know that's a linear function that looks like so. So again, as x approaches infinity, the y value is going to approach infinity. But folks, further analysis will reveal that this e to the x is rising faster than the linear function y equals x. Therefore, you could say that this is always going to be larger than the second term. Therefore, this limit will be infinity. Perhaps this is a good time to review what I call the list. And the list compares each of these very common functions in terms of how fast they go to infinity. So it turns out that these growth functions, e to the x, which we just saw, 2 to the x, growth functions are going to grow faster than x raised to some integer p, which in turn are going to grow faster than the natural log of x. So in other words, the natural log of x is the slowest out of these functions. Remember, the natural log of x does something like this. Okay, whereas x squared is going to go like this. And e to the x is going to go like that. So it turns out this is rising faster than that, which is rising faster than the natural log of x. And by the way, this could even be x raised to a fraction. So not only does it apply when you have x squared, but even if you have x to the 1/3 power, that's going to rise faster than natural log of x. So let's look at this in practical terms. Suppose we have the limit as x approaches infinity of x minus ln of x. So as x approaches infinity, we're going to have infinity minus infinity. Again, that's indeterminate. But if we come to our list, we see that this is faster than ln of x. Therefore, that is going to head towards infinity. However, if we have a reversal, suppose we have the limit as x approaches infinity of a slower function first. Let's say we have x squared minus e to the x. This is going to be slower than e to the x. Therefore, e to the x is always going to be larger than the first term. Therefore, if you're subtracting a larger value from that first term, this is going to head towards negative infinity. So this sequence of how fast functions rise, growth functions are the fastest. X raised to an integer are in the middle, and the natural log of x is the slowest. This sequence is very valuable in helping us determine the limits of indeterminate forms. I just want to clear up some confusion about what I said earlier. I kept saying that p is an integer, but it does not have to be an integer. It has to just be a positive number. So just think of p for positive. Even if you have x to the 1/3 power, it's still going to overtake the natural log of x. Let's look at Desmos here. And you could see that I have y equals ln of x here in blue, and y equals x to the 5th power shown here. You could see clearly that x to the 5th rises faster than ln of x. But here, if I graph y equals x to the 1/3 in red, it appears that the red values are below the blue. But if you keep going, you have to trust me that that red line eventually goes over the blue line. We have the limit as x approaches infinity of this rational function with polynomials on the top and the bottom. There's two ways to do this. One way is to recognize that when x is headed towards infinity, we're talking about end behavior, either infinity or negative infinity. So if you were given this in pre-calculus and you were asked to find the end behavior of this function, that is tantamount to finding the horizontal asymptote. So when we find the horizontal asymptote of a polynomial expression over a polynomial expression, we look at the degree in the numerator versus the degree in the denominator. So remember, if it's even, then it's the ratio of the coefficients. So we already know that this function is going to have a horizontal asymptote at y equals 2. So whatever this function does, it's going to end up with end behavior approaching 2. So that is the limit. But suppose for some reason your teacher said, okay, we're not allowing you to use that technique. This is the algebraic way of doing it. You go to the denominator and you find the highest degree, and you divide the entire numerator and denominator by the highest degree in the denominator. So the highest degree in the denominator is x squared. So we're going to come along and we're going to divide it one term at a time by x squared in the denominator, and we're going to do the same thing in the numerator. And then we're going to plug in infinity. So down here, x squared over x squared just becomes a 1. Now, if you plug in infinity down here, this x is going to cancel out. You're still going to have an x here. If you put a very large number in here, say 8 over 1 million, that is approaching 0. So anything that's going to have a big number, namely infinity, in the denominator is going to go to 0. So that's going to go to 0, that's going to go to 0. Now as we make our way up to the numerator, that's going to go to 0, that's going to go to 0. These are going to cancel out, and you're going to end up with 2 over 1. We have another polynomial rational expression heading towards infinity. If you want to get the end behavior of this, we see that this rational function is top-heavy. When the rational function is top-heavy, namely the degree of the numerator is higher than the denominator, there is no horizontal asymptote. Rather, there's oblique asymptotes, and the graph heads towards, the y value of the graph is going to follow the oblique asymptote towards infinity in this particular case. Now, if you want to do it algebraically, you're going to follow the same rule. You're going to go to the denominator, find the highest degree, and divide all the terms everywhere by the highest degree in the denominator. So we're going to divide both of these terms by x squared, same thing up top. When we do that, and we plug in infinity, we know that that goes to 0. X squared over x squared is going to go to 1, so we're going to have 1 in the denominator. In the numerator, this is going to go to 0 because it's bottom heavy, and here the x cubed and the x squared, they're going to cancel out. You're going to have 4x on the top. So when you plug in infinity into this fraction, you could see that this limit is heading towards infinity. Next, we have the limit as x approaches infinity of radical 2x plus 3 minus radical x minus 1. So again, folks, we're going to use the conjugate. I went ahead and did that ahead of time. So when we multiply radical 2x plus 3 times radical 2x plus 3, the radical goes away. We get 2x plus 3. Middle terms drop out. We have a minus sign, and then we end up with x minus 1. We distribute that minus sign, and we end up with x plus 4 in the numerator. Now, in terms of the denominator here, one of the benefits of working with limits that go to infinity is that you can ignore this plus 3 and just consider the radical 2x as the important component. Here then I gave the radical 2 and x its own separate radical, pulled out square root of x, and we're left with this expression here. Now this is top heavy, but it's not top heavy by 1, which means there is no horizontal asymptote and there's no oblique asymptote. So what we do in this scenario is we divide by the largest degree in the denominator, and we do that with all the terms. And when we do that, we realize that this is going to go to 1 down below, and here that's going to go to 0, and we're left with this expression. If we bring that x to the 1/2 to the numerator, we end up with x to the 1/2 on top, And then we have this coefficient on the bottom, which really doesn't play a role. So now if we go ahead and plug in an infinity to this numerator, the overall limit is going to be infinity. Folks, let's look at the intuition of a couple limits that we've done recently. The first one was x goes to infinity with these two radicals, and we ended up with 0 as our answer. And with this one, we ended up infinity as our answer. So both of them started out as infinity minus infinity. One ended up 0, the other one ended up infinity. So what's going on here? Well, it turns out that these are relatively close in value. So this is like almost, subtracting 5 minus 4.9999, very, very small number, it's close to 0. Here, however, this one is significantly bigger than the second term. And that's why if you have the bigger term minus subtracting from that a smaller term, you're going to head towards infinity. So the fact is, not all infinities are the same size. That's why it's indeterminate. That's why you have to do some algebraic manipulation. Next, we have this limit that involves quadratics under the radical. And it's really difficult to apply any intuition here. You don't know, you have 2x squareds. Does this 6x make this significantly larger enough to call this an infinity limit, or are they close enough together that it would be 0? So here we have to do the algebraic manipulation, and we know that to be multiplying by the conjugate. So if we do that, the radicals go away, and you have a minus sign. Distribute the minus sign, and you get the following. Okay, folks, now here's where it gets interesting when you're dealing with radicals. We're going to divide by the highest degree in the denominator. So here we would be dividing by x squared. But that x squared is under a radical, so we're not really dividing by x squared. What we're doing is we're multiplying by 1 over x outside of the radical. So if we were to bring this 1 over x into the radical, that would become an x squared. And the way I think about it is when you go in the radical, you get bigger. So if you're moving that in the radical, that x to the first becomes x squared. Now, also of interest here is the fact that we're only dealing with positive values of x. And as we'll see on future problems, if x is going to negative infinity, we have to add a negative to compensate for this. And that has to do with what some people feel, that the square root of x squared is not x, but it's the absolute value of x. So in summary, if you're dealing with limits that are heading towards positive infinity, and you know that the values are positive, you could safely pull out a 1 over x and leave it as such. So okay, so if we multiply top and bottom by 1 over x, and when we bring that in the radical, it becomes x squared. Okay. What happens is these go to 0 because that x squared blows up that denominator. Let's take away that 1 over x because we brought it in. So now, folks, we're left with, in the denominator, square root of 1. X squared over x squared is 1. Plus square root of 1. X squared over x squared, and on top you have 6x times 1 over x. The numerator becomes 6, the denominator becomes 2. The final answer to this limit is 3. And we're going to do plenty examples of a quadratic under a radical and how to approach that. On this next limit, we have x going to infinity of natural log of x squared over x. So if we come to our list here, we see that the natural log of x is slower, and that's even true if you take it to the second power. In fact, let's look at it quickly on Desmos, and you can see here that ln of x squared just simply involves taking that negative component that approaches negative infinity, and because we're squaring, it's going to be positive and it's going to go up towards positive infinity, but you could see the ascent of ln of x is still relatively flat, and that of y equals x is much faster. So we'll use that to our advantage to know that this is going to grow much, much faster, and this limit is going to go to 0. Now, in case you don't believe that, you could also do L'Hopital's rule here, because initially, excuse me, we do have infinity over infinity. If we take the derivative of the numerator, we're going to use the power rule, so we're going to have 2 ln of x, and then the chain rule means we need to take the derivative of what's in the parentheses. On the bottom, we're just going to have 1. Okay, so here now we're going to have 2 ln of x over x. This is still infinity over infinity, so we're going to employ L'Hopital's rule again, and we're going to get 2 times 1 over x divided by 1. This is going to end up just being 2 over x, and if we envision infinity being in the denominator, this is going to go to 0. Let's use our list here to do these 3 limits that head towards infinity. First, we have natural log of x over x to the 1/3 power. So even though that's a fraction, as long as it's positive, it's going to be faster than ln of x. So if this is growing very, very fast, we're going to have a huge number down below compared to a smaller number. Think about 1 over 100,000 to 1 over 1 millionth. That is heading to 0. Now down here, where the roles are reversed, we have the faster function up here. That means this is going to grow from 1,000 to 10,000, etc. That's going to be infinity. Now down below, we have x to the 6th on top, but on the bottom, we have x squared plus 4 to the x. We're going to ignore the x squared and focus on the 4 to the x. This exponential function is much faster than x to the 6th. So we're going to get a big, big number here. That's going to head towards 0. Next, we have the limit of 6 to the x over 2 to the x plus x to the 4th. So in the denominator, the 2 to the x is going to dominate that polynomial. And we could do the reverse power rule here and do 6 over 2 raised to the x. That's 3 to the x, and that's going to go to infinity. Now down below, to do this limit, we have to extend our list to include the factorial function, which is very fast. Not quite as fast as x to the x. So down here, this is going to be x factorial over xp. That's going to dominate, and we're going to get infinity. Let's take a quick look on Desmos at these 2 unique functions. The first is x factorial. You could see it's this wild function here when x is negative, but as x approaches infinity, you see that the y value heads towards infinity. For y to the x, this thing is just a rocket from the get-go. It just goes straight up. So this is the fastest function that I think you'll see in a typical calculus limit. Next, we have the limit as x approaches infinity of ln of x minus the square root of x. So here, we're going to have an infinity minus infinity situation. Now, I've seen sometimes where you're not allowed to use intuition in this scenario, and other times that you can. The intuition here would be that ln of x is going to be smaller than x to the 1/2, as you could see from our list here, which means we're going to have a small minus big situation. So envision a small number like 3 minus a bigger number, a huge number, and you're going to go towards negative infinity. But if you're uncomfortable using the intuition here, and I don't blame you because I am, we can do the following. We can pull out the square root of x as a greatest common factor. You want to pull out the dominant factor in this situation. So that would leave inside the parentheses ln of x over the square root of x minus 1. Now we could very comfortably apply the list here. This is going to grow much faster than that, so that's going to go to 0. Now we have square root of x times minus 1 minus square root of x, and as x goes to infinity, this will go to negative infinity. Next, we have the limit of, as x approaches infinity, of e to the x minus x raised to the e power. So all this is, folks, is just x to the 2.7 power. So that fits in that position on the list. So you could see e to the x is faster than x to the e, which means that we're going to have a big minus small situation, and we have big minus small situation getting bigger and bigger, then you're going to go to positive infinity. But again, if you're not comfortable using intuition in an infinity minus infinity situation, let's pull out the dominant of these two terms, and that would be e to the x. That's going to leave us with the following inside the parentheses. Here, clearly, e to the x, which is in this position, is going to be faster than x to the e, which is in this position. If the denominator is going really, really fast, larger number, that's going to go to 0. We're going to have e to the x. And the limit as x approaches infinity of e to the x is positive infinity. Next, we have the limit as x approaches infinity of negative x divided by x cubed. So we could use the list here and recognize that e to the x is a version of 2 to the x and will go faster than x cubed, which means the numerator will manifest, go to infinity, and then be turned into negative infinity. So that is your answer. Folks, the other way to do this is to recognize that we have negative infinity over infinity to start with, and that is L'Hopital's friendly. So if we went ahead and took the derivative of the top and the bottom, again, we are not using the quotient rule. The top is going to stay negative e to the x. Using the power rule down below, we're going to get 3x squared. We're going to do this again, negative e to the x over 6x, and again, negative e to the x over 6. And at this point, it's clear that that limit is negative infinity. Next, we have the limit as x approaches infinity of negative x to the 4th power over e to the x minus 2. So e to the x is faster than x to the 4th. Therefore, this denominator will dominate. So as this explodes to infinity, this fraction goes to 0, and the final limit is negative 2. Folks, anytime we have infinity or negative infinity in the denominator with a constant up top, that fraction is going to go to 0. For this limit, we see that x is going towards negative infinity, which means the inputs into x are going to be negative. So if we have e to a negative number, we can look at e as e over 1, and then we could flip the fraction and then change the sign of the exponent. Now when we do the power rule, we're going to have 1 over e to the x, and this is going to be a number that is less than 1. Therefore, this itself is a decay function. And decay functions are going to move towards the horizontal asymptote. And here, the horizontal asymptote is going to be negative 5. So this graph would do something like this. So this limit is going to be -5. Another way to think of it is that this would just go to 0. Down below, we're going to rewrite this as -1 times e to the x plus 1. So this is still a growth function because the base is positive. However, that negative causes a reflection over the x-axis. So here our horizontal asymptote is going to be +1. We're going to have a growth function in that it moves away from the horizontal asymptote as we move left to right, but it does so beneath the line y equals 1. So this y value is headed towards -infinity, and that's our limit for this example. For this limit, we can think of this entire entity as e to the -3x over 1. We could then take this whole e to the 3x and move it down to the denominator. And when we do that, when we cross the fraction line, we change the sign of the exponent. So this becomes e to the +3x in the denominator with a 1 on top. When we plug in infinity down here, this number is going to get huge, which means this whole thing is going to go to 0. So our limit here is just going to be -1. For the next limit, we're going to bring back our list. And remember that e to the x, which is going to be represented over here, similar to 2 to the x, is going to grow much faster than the x to the 5th. Therefore, this whole limit is going to head towards infinity. Finally, with this last limit, we're going to do the same thing that we did with the first one. We're going to take this and bring it down, and when we cross the fraction line, we change the sign of the exponent. So this becomes e to the +5x. And when we go towards infinity, looking at our list, this is going to go much, much faster than the numerator. Therefore, this whole entity is headed towards 0. Next, we have the limit as x approaches 0 from the right of this rational function. So if we try to plug in 0, we're going to get 4 on the top. And on the bottom, we're going to get 0. Now, we can't factor the top. So I'm going to try to solve this limit using intuition. Okay, if we plug in 0 on the top, we're going to get 4. Now, the fact that this is a sided limit coming from the right, we know that as we approach 0, we're going to have very small positive numbers here. So here, let's look at the number line really quickly. When we have 0 coming from the right, we're going to have 1/10, 1/100th, and if we get really close, we're going to have 1 over 10,000 or 10 million. Big, big numbers. Okay. For the sign of x approaches 0 from the positive side. If we look at the unit circle, if that's 0 degrees and we're approaching from the positive side towards 0, again, we're going to have very, very small positive numbers. So let's just put 3 over 1,000,000 here. Then if we do keep change, if we add these together, we're going to get a huge positive number. That's a fraction. And when we do keep change flip, this is going to go to positive infinity. For example, let's say you had 4 over 1 over a huge number like this. So that's going to be 4 over 1 times something like this. Keep change flip, and you're going to get positive infinity. Next, let's solve this again using intuition. If we plug in 3 on the top, we're able to do that. We're going to get 2 times 9 is 18 plus 8 is 26. Now let's focus over here. If we're approaching 3 from the left, then the numbers are smaller than 3. So even if we have 2.99 squared, it's going to be smaller than 3. And when we square that, it's going to be smaller than 9. So we're going to get very, very small negative numbers here. Okay, something like this, for example, 8.9999 minus 9. And if you were to compute this, you would get a very, very small negative number. And when you do keep, change, flip, you're going to get negative infinity. Next, we have the limit as x approaches negative 1 from the right of 3x divided by x plus 1. I feel that a number line is always helpful in this scenario. So let's do a number line, and here's negative 1. So we're approaching negative 1 from the right. So as we get close to negative 1, let's say we have negative 0.999, and we add a 1 to it, this is always going to be positive and very, very small. Whenever you're combining a negative number and a positive number, you do big minus small. So if we do 1.00 minus 0.999, we're going to get 0.001, and it's going to be positive because we take the sign of the bigger number when we do big minus small. And that could be written as 1 over a big number. So when we insert that in the denominator and we do keep, change, flip, this is going to come up in the numerator. Now that x is going to be negative, approaching negative 1. In fact, we could just plug it in there. So we have negative 3 times a big, big number that used to be the denominator down here. And then, therefore, this entire limit is going to approach negative infinity as our final answer. Next, we have the limit as x approaches negative 2 from the left of 2 divided by x squared minus 4. So if we go to the number line, and here's negative 2, as we approach from the left, we see that we're going to have negative 2.001, for example, just beyond the negative 2. So if we square that, that's going to become a positive number that's a little bit bigger than 4. So let's do something like that. So when you subtract 4 from that, you're going to get a positive, very, very small number, such as 0.001. We're going to change that to 1 over a big number. And when that goes in the denominator, and we do keep, change, flip, this denominator of the denominator ends up in the numerator, and we're going to get to positive infinity as the answer of this limit. Here we have the limit as x approaches 3 from the right of x minus 2 over this polynomial. We could go ahead and factor the quadratic equation down below and get x minus 2 times x minus 3. We can cross these two factors out, and we're left with the limit as x approaches 3 from the right of 1 over x minus 3. So if we're approaching 3 from the right, we're talking about numbers that are slightly bigger than 3. And when we subtract a number that's bigger than 3, when we subtract 3 from it, we're going to get a very, very small positive number in the denominator. We're going to do keep, change, flip, and this limit is going to go to positive infinity. For this limit, let's get the intuition as to what's happening with this rational function. So if we factor the denominator, we're going to have the following. So we know there's going to be a vertical asymptote here and a vertical asymptote there. So let's look at the vertical asymptote at x equals positive 2, because that's where our limit is heading. The fact that that is an odd exponent means that this vertical asymptote, as the graph approaches from both the left and the right, it's going to be going in different directions. So it's either going to be like that in yellow, or it's going to be like this in red. Either way, as you approach that 2, as you approach that vertical asymptote, we know that this graph is going to be headed in different directions. Therefore, we know that this limit does not exist. Next, we have this two-sided limit and another rational function. If we look at the denominator, we can see that this becomes x plus 1 to the second power. Now, we know there's going to be a horizontal asymptote at y equals 0 because it's bottom heavy, but we're not heading towards infinity. We're not looking towards or looking for end behavior. So we know we're going to have a horizontal asymptote at x equals -1, but unlike, a previous limit where we had an odd exponent associated with the vertical asymptote, this is an even. That means our graph is going to approach this vertical asymptote in the same direction. It's either going to be positive infinity or negative infinity. So we know we're looking at some sort of graph that when x equals -1, we're either going to be having this situation or in green or this situation. So the idea to differentiate between whether we have an orange situation and our limit is heading towards infinity versus green where our y value is heading towards negative infinity, we just need to figure out what is our graph, what's the y value of our graph when x equals -1. So we just need to plug in -1 into this function. If it's positive, we're going to have the orange situation. If it's negative, we're going to have the green situation. Folks, when you plug in values to a rational function, when you graph, you don't even need to plug in down here because that's squared. That's always going to be positive. So really what you're plugging in to is 3x. That's going to be negative. Therefore, this is our scenario and our limit is -infinity. Now, there are some teachers that will say that that is a limit that does not exist. I've seen it both ways on the internet, that the limit is -infinity or the limit does not exist. Depends on your teacher.
Next, we have the limit as x approaches 3 from both sides of the floor function of x. Recall, the floor function is also known as the greatest integer function, and the idea, folks, is to round down or to the left to the next integer. So here, the floor function of positive 3.7, we would go left, round down to the nearest integer, which is 3. Here, with -2.3, we're going to round to the left. We're going to round down to the nearest integer. This would equal -3. So here, because this is a two-sided limit, we're going to be approaching 3 from both directions. So if we have 2, 3, and 4 listed, let's first take the limit of the floor function as x approaches 3 from the left. So here, as x approaches 3 from the left, we're at 2.3, 2.4, 2.8. That's going to round down and be 2. However, if we approach 3 from the right using the floor function, then we're going to have 3.4, 3.2. As we approach 3, we're always going to have a 3 point something, and that's going to round down to 3. Since these limits do not concur, since they are not the same from the left and from the right, this limit does not exist. So we have the limit as x approaches 1, a two-sided limit, a normal limit, with a combination of the absolute value of x and the floor function. Now, folks, as x approaches 1 from either side, x is still going to be positive. So this inside is always going to be positive during the course of this limit. So we can remove the absolute value sign because we're always going to be dealing with x as is. Okay, now in terms of the floor function, it's going to be different as you approach both sides of 1. So we already know this is going to be a do not exist. So let's just go ahead and go through the motions. Let's first do the limit as x approaches 1 from the left. As x approaches 1 from the left, this is going to still be 1. And as x approaches 1 from the left in terms of the floor function, we're going to have decimals 0.5, 0.6, 0.7. All of them are going to round to 0, so that limit is going to be 1. Next, we're going to do the limit as x approaches 1 from the right. Again, x approaches 1 from the right, this limit is still going to be 1. However, dealing with the floor function now, if we're approaching 1 from the right, we're talking about 1.5, 1.4, 1.1. Any of these are going to round down to 1. So we're going to get 1 plus 1 equals 2. And as predicted, the limit does not exist.
Next, we have the limit as x approaches 0 of the floor function of x divided by x. So here, if we try to plug in the floor function of 0, that is just going to be 0 over 0, and that is indeterminate. We cannot do derivatives here. We can't use L'Hopital's. So in this instance, we're going to have to treat this as a two-sided limit. So let's first start from the left. So if we draw our number line and we have 0, -1, as we approach 0 from the left, we're going to be at numbers like -1/10, -1 over 1,000, etc. So the floor function is going to move left to -1, and the x value is going to be one of these very, very small negative fractions, such as this. So when we evaluate this, this is going to go to positive, this is going to go to the numerator, and we're going to get positive infinity. Now let's look at the limit as x approaches 0 from the right of the floor function of x divided by x. So with respect to the floor function, as we approach from the right, we're going to get numbers like 1 over 1,000th. The floor function is going to revert to 0. The denominator is going to be a very, very small positive number, and when we do keep change flip, we're going to get 0. So because these do not match, this limit does not exist. Folks, the convention whether to say the limit is undefined or does not exist, I've seen it described differently, but I use do not exist for limits. And I might use undefined when I'm talking about the x value when there's a vertical asymptote. But for limits, I tend to use does not exist, DNE. And the way I remember that is that we have to set limits on the amount of donuts that we eat. So with limits, donuts, DNE does not exist. Next, we have the limit as x approaches 1 of 2 minus the floor function of -x divided by 2. So folks, in this case, you are allowed to plug this 1 directly into this fraction and then create the floor function of -1/2 and then proceed from there. So here, if this is -1/2 and here's -1, the floor function of -1/2 is going to revert to -1, and we're going to have 2 minus -1 equals 3. In other words, folks, we do not have to do the two-sided limit. Here's what you don't do. What you don't do is say to yourself, okay, well, the floor function of x, when you plug in 1, going to 1 is going to be different whether you're going from the left or the right. You don't do that. You do not create a left and right approach to 1. Rather, you're allowed to plug it right in, evaluate that fraction, and then apply the floor function to the fraction. Folks, we recall during our discussions about compound interest that this was the formula to determine the amount after a certain amount of time when a principal was growing at a compound rate of r, and this compound rate is applied n times per year. So if the rate was applied monthly, n would be 12. If it was weekly, n would be 52. But remember, there were other problems where the growth was continuous. So we would envision that n value going to infinity. When we did that, we were able to use this formula where the amount equals the principal times e raised to the RT power. So in other words, out of this original formula, only the r and the t survive. Folks, I want you to memorize this limit because it's going to be helpful. So here, let's first do it in terms of n. With n going to infinity, that means we're compounding continuously. The only thing that survives are the r and the t. So here, if we have the limit as x approaches infinity, now we're going to use x instead of n as in Nancy. The only thing that's going to survive are going to be the r and the t. Let's see how this can be helpful. Let's now apply this to this first limit. So we see x is approaching infinity, and we're saying to ourselves, okay, this looks like the compound interest formula. We have x here and x here. So what we want to change this to in our minds is 1 plus 1/2 over x raised to the x times 1. So now, folks, we've identified our r value and our t value. Those are the only entities that are going to survive. So we're going to have e to the 1/2 times 1, which is going to equal e to the 1/2. And if you want, you could change that to the square root of e. That is your final limit. Next, we have the limit as x approaches infinity to 1 minus 1 over x raised to the x. So we recognize this as this formula over here in disguise. So let's change this to 1 plus negative 1 over x raised to the x times 1. Folks, there's your r, there's your t. Those are the only entities that survive. E to the negative 1 over e is your final answer. We have the limit as x approaches infinity of 1 minus 1 over x raised to the x squared. So we're going to write this as 1 plus minus 1 over x times x times x. So folks, the only two entities that are going to survive are the numerator there and that x. So we're going to change this to e to the negative 1 times x equals e to the negative x. So now we can rewrite this as 1 over e to the x, and as x goes to infinity, this is going to be a decay function, and decay functions, as you know, approach the horizontal asymptote. So this final limit is going to be 0. Next, we are given that the limit as x approaches infinity of x divided by x plus 2, all raised to the x power. So what clues us in, folks, that we're going to use this compound interest technique is that there's an x up here in the exponent. Okay, so right now, we don't have a splitting of this fraction. So this is a nice trick. We're going to change this to x plus 2 over x, and then we're going to change the sign of the exponent. So you could flip the fraction and change the sign of the exponent. And when we do that now, we could separate this fraction. So we can have x over x plus 2 over x raised to the negative x. And if we continue, now we're going to have 1 plus 2 over x raised to the negative 1 times x. So now, folks, this fits this pattern. So you could see here that we have the limit as x approaches infinity of 1 plus r over x. Here's our r raised to the xt. Here's our r, and here's our t. So our final answer is going to be e to the r x. Okay, so the only thing that survives, I'm sorry, it's going to be e to the rt. So the only thing that survives out of this is e to the r times t. Therefore, it's going to be e to the negative 2, otherwise known as 1 over e squared.
Next, we have this limit as it approaches 0. And we recognize this as the difference between two perfect squares in the numerator and the difference between two perfect cubes in the denominator. And these a's and b's are not the same, it's just for illustrative purposes. Okay, so if we have difference between two perfect squares, we know we're going to have a plus b times a minus b. Sorry about that. And on the bottom, we're going to have a minus b, a squared plus ab plus b squared. And the way I remember that is this is the same as the original, this is the opposite, and this is always positive. SOAP. Same, opposite, always positive. Okay, if we go ahead and plug in, then in the numerator, we're going to have our a is 1 plus x plus 1 and 1 plus x minus 1. In the denominator, our a value is going to be 1 plus x and then our b value is going to be 1. And now we're going to have a squared, which is 1 plus x squared, plus a times b, which is x plus 1 times 1, and then plus b squared, which is 1 squared. Okay, let's make some room here. Thank you for your patience. Okay, so for the numerator, this is going to simplify to 1 plus x plus 1 times 1 plus x minus 1, or continuing along with the numerator, x plus 2 times x. For the denominator, this is going to become x. And here, if we FOIL out 1 plus x squared, we're going to have x squared plus 2x plus 1. And then we're going to have plus x plus 1 plus 1. This is going to simplify to x times, let's see, x squared plus 3x plus 3. Okay, folks, now we have an x on top and x on the bottom. We're going to cancel those out, and then we are left with the limit as x approaches 0 of, in the numerator, x plus 2 over x squared plus 3x plus 3. And here we can insert 0 in for our x's. One way to do that is to just put your thumb over any term that has an x in it, and we end up with 2 over 3 as this limit.
Next, we have the limit as x approaches 8 of the cube root of x minus 2 over x minus 8. If we were to plug in 8, the cube root of 8 is 2. We would get 2 minus 2 or 0, and 8 minus 8, 0 over 0. So folks, the key to this problem is to recognize that this is a hidden difference between two perfect cubes. So I think it's easier to change to fractional exponents. So let's change the numerator to x to the 1/3 power. And in the bottom, this is going to be, a cubed minus b cubed, where a equals x to the 1/3 and b equals 2. So you could see if you have x to the 1/3 cubed, you're going to get a. If you get x to the 1/3 cubed, you're going to get x, and if you have 2 cubed, you're going to get 8. Okay, so what we're going to do here is we're going to change this to a minus b times a squared plus ab plus b squared. Same, opposite, always positive, SOAP. Okay, so let's do a minus b. That's going to be x to the 1/3 minus 2. And already we're smiling because we see that in the numerator. Okay, a squared is going to be x to the 1/3 raised to the second power. Okay, let's do that on the side here. X to the 1/3 raised to the second power. That's the power rule. So we're going to get x to the 2/3. Then we're going to add these two multiplied by each other. We're going to get 2x to the 1/3. And finally, we're going to add 2 to the second power, otherwise known as 4. Okay, so as advertised, we can cancel out these two, and we are left with plugging in what we see in the denominator. Okay, so let's look at what we have. Let's make this a little neater. And this is what we ended up with. Okay, so if we plug in 8 to these two terms here, we're going to get 8 to the 2/3 power plus 2 times 8 to the 1/3 power plus 4. Okay, 8 to the 2/3 power is the same thing as the cubed root of 8 squared. And the way I remember this is that this on the bottom is the root. Just like trees have the roots underground, the root is located underneath the fraction line. So that's your root, cubed root, and then you square it. So the cubed root of 8 is 2. 2 to the second power is 4. Okay, here, this next term, we have 2 times the cube root of 8. We know the cube root of 8 is 2. 2 times 2 is 4. And then we have the other 4. The final answer is 1/12. We have this limit as x approaches 9 of this complex radical within a radical in the numerator, and x minus 9 in the denominator. If we try to plug 9 directly, we get 0/0. So here, even though this is more complex, this to me is screaming out that we're going to use the conjugate. So if we're going to use the conjugate, we're going to be multiplying radicals. Let's go ahead and switch to the fractional exponent version of this expression. So when we do that, we still have the radical on the inside the parentheses, but we have the 1/2 on the outside, and we can work with that. So let's go ahead and multiply top and bottom by 1 square root of x to the 1/2 plus 2. Do that on both top and bottom. Okay, as usual, we're going to leave this alone. We're not going to distribute anything in the denominator. And when we do that, we're going to multiply these first two terms. And when you multiply two entities and the base is the same, okay, so this base is the same as this base. This is no different than multiplying x to the 1/2 times x to the 1/2. The rule is you keep the base and you add the exponents. So we're going to keep the base and we're going to add the exponents, and we're going to end up with simply 1 plus the square root of x to the first power. And then we're not going to do the middle steps because we know the middle term will drop out. And then we're going to multiply -2 times +2 and get -4. All right, I'm going to leave the denominator alone for a second. And here we're going to get the square root of x minus 3 on top. Now, let's take a look closely at x minus 9. Folks, that's a hidden difference between two perfect squares. So this is going to nicely convert to square root of x plus 3, square root of x minus 3. That's going to allow us to cancel out these two terms. Let's make some room here. Okay. We're now going to end up with, I know it's hard to keep track of all this, but we're going to have 1 in the numerator, plus 1 in the numerator, and then we're going to have these two terms in the denominator. Okay, now we're able to plug in 9. So down below, we're going to have 1 plus the square root of 9, which is 3, raised to the 1/2 power. That's 4 to the 1/2 power. That's the square root of 4, and that's 2. So this becomes 2 plus 2. Here, this is the square root of 9, which is 3. 3 plus 3 is 6. We're going to have 1 over 4 times 6. This final limit is going to be 1 over 24. We next have the limit as x approaches infinity of x to the 4th divided by e to the x minus 2. So if we use our list, we know that e to the x is a lot faster than x to the 4th. So this is going to go to 0, and our final limit is going to be -2. We have the limit as x approaches -2 of this rational function, and we cannot plug in -2 because the denominator will be 0. So in this case, we look to factor the numerator, and we are unable to do so. So another trick you can use in this scenario is long division. So there's two ways to do long division. One, you could drop the dividend into the box, but when you do that, you have to remember to add 0 for the x squared term. The other way to do this is to use synthetic division. So if you're going to use synthetic division, you look at the divisor, you set that equal to 0, you solve for x, you get -2. It's -2 that goes into this little box here. Then we take the coefficients of the polynomial in the numerator, and that's going to be 1. Don't forget the 0, -5, and -2. To do long division, we drop this straight down, and then we multiply and we add. So now we're multiplying, now we're going to add. We're multiplying, we're going to add. We're multiplying, and we're going to add. The fact that you get 0 means that this is going to be a factor. This and that are going to be factors. We downgrade this to x squared minus 2x minus 1. Now you can plug in -2 here, and your limit is 7. Next, we have the limit as x approaches 5 of this rational function that contains a complex fraction in the numerator. And the way to approach these is to use what I call a bomb on the top that's going to blow out both of these denominators. So here we're going to multiply by the two denominators multiplied together on top. So if we're going to do that on the top and knock out these denominators, we have to do the same on the bottom. This way we're multiplying by just 1. Okay, so now we're going to distribute this bomb, like I call it, into this expression here. Okay, so if you want, you could put your finger over the x plus 2 and the x plus 2, and you're left with 7. Then, when you multiply the second term, you have your minus sign. Now you're going to put your finger over that 7 and that 7, and you're going to have the minus sign distributing into the x plus 2. Like so. Excuse me. On the bottom, we're going to have all three factors, x minus 5, 7, and x plus 2. And the hope here is that the x minus 5 is going to cancel out. When we simplify the numerator, we're going to have 7 minus x minus 2. The numerator is then going to become minus x plus 5. Now, minus x plus 5 and x minus 5 can be canceled out with a -1 resulting. So let's go ahead and do that. So we're going to cancel that and that. We're going to be left with -1. That's going to allow us to then plug in the 5 here, and our final limit answer is going to be -1 over 49. Next, we have the limit as x approaches 5 of this rational function with a complex fraction. So again, we're going to use the Baum technique. So we're going to multiply on the top by x squared times 25, and we're going to do the same on the bottom. Let's leave it as 25x squared on the bottom. Okay, on the top, when we distribute, first we're going to put our thumb over the x squareds, and that's going to distribute and give us 25 for the first term. Then for the second term, as we distribute the -1 over 25, we're going to put our thumb over the 25s, and we're going to end up with -x squared. Folks, we recognize, again, we're going to have a situation where these two are going to cancel out, and we're going to get -1. And on the bottom, we're going to get 25x squared. We can go ahead and plug in now the 5 into the x squared. It's going to be -1 over 25 squared, otherwise known as -1 over 625. Here for this limit, as x approaches -2, we are unable to factor and cancel. So folks, what we're going to do is we're going to use long division here. All right, let's do synthetic division. Okay, since our factor is x plus 2, we're going to put -2 in the little box. And across the top here, we're going to have 1 for the x cubed. We're going to have 0 for the missing x squared, -5 for the x term, and -2 for the constant term. We're going to bring this straight down. We're going to multiply, then add. Multiply, then add. Multiply, then add. The fact that we get 0 here means there's no remainder, and that this is the second factor. So on the top, we're going to have x squared minus 2x minus 1 as the other factor, and that times that would give us the dividend. Okay, so now what we can do is we could just plug -2 right in here. So -2 to the second power is going to be +4. -2 times -2 is +4 minus 1. We're going to have 8 minus 1. The final answer to this limit after this long division is +7. As we move into limits for trigonometric function, I want to point out the big 5 limits that you just have to memorize. All of them have x in the denominator to start, and as we'll see, there's going to be offshoots of the first two. Okay, the first one you have to memorize is that the limit as x approaches 0 of sine of x over x equals 1. Now, the fact that this limit equals 1 means the numerator and denominator have to be the same. So it turns out that there's an offshoot of this, and that is that the limit as x approaches 0 of x over sine of x is also equal to 1. Okay, the second one you have to memorize is that the limit as x approaches 0 of 1 minus cosine of x over x equals 0. And the fact that you get 0 here means that this minus that gives us 0, which means 1 and cosine of x have to equal the same. So we could flip these and say this: the cosine of x minus 1 over x equals 0, and that's an offshoot limit. In other words, the limit as x approaches 0 of these two terms switched is also going to give you 0. The last one is that the limit as x approaches infinity of sine x over x equals 0. Now this is the only one I'm going to do a small proof of. If you come over here, we see that the sine of x, the y value, is always going to be less than 1 and greater than negative 1. If we come along and we divide all of these by x, so you see this is the limit we are talking about. Now, if you go ahead and take the limit of each of these three as x approaches infinity, we know that that goes to 0 and that goes to 0. So you have the sine of x over x being located between 0 and 0. This is known as the squeeze theorem. So if this is less than or equal to 0 and greater than or equal to 0 at the same time, then the limit has to be 0. Next we have the limit as x approaches 0 of 1 minus cosine of x over sine of x. So we know if we plug in 0 here that the sine of 0 is 0, so we're going to have to do some sort of algebraic manipulation. What's jumping out at me here is to use the conjugate. Because anytime you can introduce sine squared, cosine squared, you're hoping that you can use the Pythagorean identity that sine squared x plus cosine squared x equals 1. So let's see what happens here. Of course, we have to do both top and bottom because we're multiplying by 1 if we do so. So on the top, we're going to create the difference between two perfect squares. And on the top, we're going to leave things as they are. We are not going to distribute or FOIL if there were two terms. We're going to leave it as is. Hopefully, we'll get some cancellations here. So here, if we take this cosine squared x and move it to the other side, we could see that we can replace this numerator with sine squared x. So let's go ahead and do that down here. We have sine squared x over sine x times 1 plus cosine x. And indeed, if we have sine squared x on the top, sine of x on the bottom, this reduces to just sine x in the numerator, and then we have 1 plus cosine x in the denominator. Now, if we plug in 0, the sine of 0 is 0. We're going to have 1 plus cosine of 0. The cosine of 0 degrees is 1. That's 0 over 2. Our final answer is 0. We have the limit as x approaches infinity of the cosine of the inverse tangent of x. So the question is, can we bring this limit inside? So let's investigate that. We can only do that if in fact this limit exists. So let's try that. So we're going to have the limit as x approaches infinity of the inverse tangent of x. Now, if we have the inverse tangent of x, let's try plugging in infinity here. The inverse tangent of infinity equals what? We could change that to the tangent of what equals infinity. So in other words, this argument becomes the solution, and this solution becomes the argument, and these switch from inverse function to normal function. Now, folks, we know from looking at the unit circle that when we see the word tangent, we think about slope. So the tangent of what angle equals positive infinity, that's right there. That's not none other than pi over 2. Sorry about that. So we have pi over 2 as our answer. So the limit does exist. Next, we could take the outer function, the cosine, and now take the cosine of pi over 2, and the answer is going to be 0. Okay, also, if you wanted to look at the inverse tangent as x approaches infinity, you could also theoretically look at the inverse tangent graph, and we know that the inverse tangent graph is going to look something like this. This is a horizontal asymptote at pi over 2 and negative pi over 2, and the inverse tangent graph does that. So as x approaches infinity, the y value approaches pi over 2. So you can either use the graph or you can use the unit circle to establish that that inside limit exists. That allows us to bring the limit inside the function and then take the cosine of that limit, which is 0. Next, we have the limit as x approaches infinity of the inverse tangent of the cosine of x. So again, we're faced with the situation where can we bring the limit to the inside? We can only do that if the limit as x approaches infinity of the inside function, which here is cosine of x, does in fact exist. But as we know, if you look at the function of the cosine of x, as x approaches infinity, the y value oscillates back and forth between -1 and +1 and does not converge to a single limit. Therefore, that inside limit does not exist. And if this inside limit does not exist, then there is no way we could take the inverse tangent of that. Now note that here, the fact that the inside limit doesn't exist, if we were able to, we could approach both sides of the limit. So for example, if we're in that situation, we have x approaching 1 and the inside limit does not exist with some other function, then we would take both sides. We would take as x approaches 1 from the left and then as x approaches 1 from the right to determine if we can establish the overall limit. But here, for this particular problem, the overall answer is does not exist. Next, we have the limit as x approaches infinity of the inverse cosine of this rational function. So the question is, are we allowed to bring the limit inside? So that brings us to the question is, does this limit exist as it approaches infinity? If you have a limit that's approaching infinity, we're looking at the end behavior. When you have a rational function and you're talking about end behavior, you're talking about the horizontal asymptote. So here, because the degree on the numerator and denominator are the same, this limit as x approaches infinity is going to be the ratio of the coefficients, namely square root of 3 over 2. Now we would get the same answer if we divided everything by the highest degree in the denominator. So for example, if we did this, if we came along and we divided everything in the denominator by the highest degree in the denominator and the same thing in the numerator, and then we plugged in an infinity to here, here's what would happen. So these x's would cancel out, these x's would cancel out, and when you plugged in infinity to both of these terms, this denominator is going to go way up high. So you're going to have something like 7 over a million. That's tantamount to 0, as is 3 millionths. So these go to 0, and you're going to end up with square root of 3 over 2. So the fact that this limit does exist, we can bring the limit inside and now do the inverse cosine of the square root of 3 over 2. So the square root of 3 over 2, I recognize that as quote-unquote long. Recall the way I do these is I use short equals 1/2, medium equals square root of 2 over 2, and long equals square root of 3 over 2. I then set up my unit circle. The cosine is going to refer, of course, to the x-coordinate of the point on the unit circle. So here we know that the x-coordinate is long. So we know this is what we're dealing with. That x-coordinate is long, that's square root of 3 over 2. That's short, that's 1/2. So this particular angle right there that has long as the x-coordinate, short as the y-coordinate, is none other than pi over 6. So the final answer to this limit is pi over 6. We have the limit as x approaches pi over 2 of secant x minus tangent of x. So we're going to rewrite secant as 1 over the cosine of x and tangent as sine x over cosine x. That's going to yield 1 minus sine of x over cosine x. If we try to put in pi over 2, we see that we're going to have 0 over 0. We're going to apply L'Hopital's rule and take the derivative of both. On the top, we're going to have negative cosine x, and on the bottom, we're going to have negative sine of x. And the cosine of 90 degrees is 0. The sine of 90 degrees is 1. Our final limit, folks, is 0. Next, we have the limit as x approaches 0 of the sine of 3 of x over x. So this looks very similar to one of the big five, and here it is. So the idea here is if we can get the argument of the sine function equal to the denominator, then our limit is going to equal 1. So how do we make that denominator look like that argument? Well, we would love to have a 3x down below. How do we do that? We multiply top and bottom by 3. So now we can rewrite this as the limit as x approaches 0 of 3 times sine of 3x over 3x. Now we can bring this outside the limit, and we have 3 times the limit as x approaches 0 of the sine of 3x as the argument, matching 3x as the denominator. Therefore, this matches one of the big five limits, so we're going to have 3 times 1 equals 3 as our final answer. In the limit we just did, we said at one point that the limit as x approaches 0 of sine of 3x over 3x equals 1. And we were able to say that based on one of the big five limits. In other words, we're saying that if the argument of the sine function matches the denominator, we could say it equals 1. But folks, we have to be careful. That is not always true. The sine of stuff divided by that same stuff is not always 1. So let me show you, if you're in doubt, what to do. Okay, so let's look at why the sine of 3x divided by 3x does equal 1. And then we'll look at why the limit on the bottom does not equal 1. So let's first start by letting theta equal 3x. That'll give us the limit as x approaches 0 of the sine of theta divided by theta. All I did was go to 3x. Wherever I saw 3x, I replaced it with theta. So we're going to assume that because we're having the limit of stuff over sine of stuff over stuff, this equals 1. But the problem is here the original limit has x going to 0, and we have theta inside the limit. So what we have to determine is what happens to theta as x goes to 0. So as x goes to 0, if you look at our definition of theta, theta is going to equal 3 times 0, or 0, and therefore, as x goes to 0, theta goes to 0, and the sine of theta over theta holds, because this theta is going to 0 just like the original x was. Now, let's look at this other limit. Let's see what happens. Okay, so here we have a different look of the argument. Now, all of a sudden, the x is in the denominator. Okay, so now we're going to do the same thing. We're going to say the limit as x approaches 0, and this time we're going to let theta equal 2 over x. That means we're going to have the sine of theta over theta. So all I did was everywhere I saw 2 divided by x, I replaced it with theta. Now, we can't leave the limit like this. We have to figure out what theta is doing as x goes to 0. So here we go. As x goes to 0, as x gets very, very small, theta is going to go to infinity. Now, when we do this limit, we recognize this as one of the other big 5 limits, and this limit is going to go to 0, not 1. So I have an entire video on this, when you can trust the classic limits, and I refer you to that. But typically, if the argument of the sine function or the cosine function looks like this, 3 times x, you could trust the basic limit. If x goes into the denominator, or if you have something like this, the sine of x plus 1, then you have to go through this little exercise where you convert to theta. So here we would let theta equal x plus 1, and then determine what happens to theta as x goes to 0, and determine if you can trust the classic limits. Next, we have the limit as x approaches infinity of x times the sine of 2 divided by x. So folks, we can convert this to a fraction and use L'Hopital's. So we're going to change this to sine of 2 over x divided by 1 over x. And if we put infinity here, we're going to have the sine of 0, which is 0, and then 1 over infinity, which is 0. 0 over 0 is L'Hopital's friendly. So let's go ahead and first do the derivative of the numerator. We're going to have cosine of 2 over x. And then we're going to have to take the derivative of the inside for the chain rule. So we want to take the derivative of 2 over x. That's the same thing as taking the derivative of 2 times x to the minus 1. So we're going to bring this out in front, and we're going to change that to negative 2x to the negative 2. All right, we're going to leave that alone in the numerator, and in the denominator, we're going to take the derivative of 1 over x, which is taking the derivative of x to the negative 1. We're going to pull the negative 1 out front, and we're going to get negative x to the negative 2. Now, folks, we could see that the negative x to the negative 2's cancel out, the negative signs cancel out, and we're going to end up with the limit as x approaches infinity of the cosine of 2 over x quantity times 2. So if we put infinity here for x, this is going to go to 0, so the cosine of 0 is 1. The final limit is going to equal 2. Okay, folks, it turns out there's a slightly more elegant way to do this, and that's using substitution. So we're going to do something similar to what we did when we were trying to prove whether or not the big 5 limits apply. And that is, we're going to let theta equal 2 over x. So everywhere we see a 2 over x, we're going to replace with theta. So now we're going to have the limit as x approaches infinity of x times the sine of theta. Now, what about this x here? Well, we could write x in terms of theta. All we have to do here is swap the theta and the x, and we're going to have x equals 2 divided by theta. Okay, so we're going to rewrite this as the limit as x approaches infinity. Instead of x, we're going to write 2 over theta times sine of theta. But again, folks, we have this discrepancy here. We have x going to infinity, but in our limit, we have thetas. So we have to rewrite this in terms of what's happening to theta. Okay, so we're going to have the limit as theta goes to something of 2 over theta times sine of theta. Okay, so now as x goes to infinity, what happens to theta. So as x goes to infinity, when x gets very, very, very big, theta is going to go to 0. Okay, so when we rewrite this limit, I'm going to bring this 2 out front. So we're going to have 2 times the limit as theta approaches 0 of sine of theta over theta. We recognize this as one of the big 5, which equals 1. 2 times 1 equals 2. Therefore, we get the same answer as we did when we used L'Hopital's rule. Next, we have the limit as x approaches 0 of secant of 2x. So we're going to change secant of 2x to 1 over cosine of 2x. And then we're going to go ahead and plug 0 right in there. Because the cosine of 0, recall, if you're at 0 degrees, your cosine value is the x-coordinate, which is 1. So this is just going to be 1 over 1, or 1. In this next limit, we have x going to 0 of the sine of x divided by 5x. So this looks like one of the big 5. So what we're going to do is change this to sine over x, and recall that the limit as x approaches 0 of sine of x over x, or x over sine of x, is going to equal 1. Therefore, this limit goes to 1 over 5. Next, we have the limit as x approaches 0 of sine of x times 1 minus cosine of x divided by x squared. So we recognize this as 2 of the big 5 limits hidden in here. So first we're going to have sine of x over x times 1 minus cosine x over x. So the limit of this as x goes to 0 is 1. The limit of this as x goes to 0 is 0. Both of them big 5 limits, and the end result is 0. Recall, we can take the reciprocal of that and it's still 1, and also we can reverse these and it's still 0. Next, we have another hidden big 5 limit here. We're going to break this up, and we're going to change this to sine of x over x times sine of x. Here, the limit of this as x goes to 0 is 1, and sine of 0 is 0, so we're going to have 1 times 0 is 0, and that's your final answer. Next, we have the limit as t approaches 0 of sine of 3t divided by 2t. So folks, we say to ourselves, boy, we would love it if we had sine of 3t over 3t, because we know this would then go to 1. So how do we get 3t in the denominator? Well, we multiply top and bottom by 3. So now we have the following. In the numerator, we're going to bring this 3 out front, and in the denominator, we're going to have, instead of 2 times t times 3, we're going to have 2 times 3 times t. Then we can isolate this and recognize that as one of the big 5 limits, and we're going to get 3 over 2 times 1, and our final answer is 3 over 2. Next, we have the limit as x approaches 0, sine of x squared over x. So we would love it if the argument matches the denominator. So we're going to multiply top and bottom by x, and we're going to end up with x sine of x squared over x squared. This is going to go to 1. So now we're going to have 0 times 1 equals 0. The other way to do this is to recognize you have 0 over 0, and then you could use L'Hopital's rule. Folks, again, I refer you to my separate video. The fact that the argument matches the denominator does not always mean you can use this limit. For example, This does not equal to 1. Next, we have these two limits as x approaches 0. On top, we would love to have pi x down here, because if these arguments match, then the majority of the time this will be a big 5 limit and get 1. So how do we get pi on the bottom? Well, we multiply by pi over pi. So this now becomes pi times the sine of pi x over pi x. And this version of the argument and the denominator is amenable to using the big 5 limit. This is going to go to 1, and our final answer is pi. Down below we recognize secant as 1 over cosine of x. We're going to replace secant with 1 over cosine x accordingly. Up top, we're going to multiply this fraction by a version of 1 to create a common denominator. On the top, we're going to end up with 1 minus cosine x over x, and in the denominator, we're going to have x divided by cosine of x. My mistake. This numerator is going to be 1 minus cosine of x over the common denominator that we created, cosine of x. That's what happens when the board gets too messy. Okay, now we have this complex fraction, and we see if we multiply top and bottom by cosine x, then we're left with the limit as x approaches 0 of 1 minus cosine x over x, and we recognize this as one of our big 5s. This is 0. Next, we have the limit as x approaches infinity of the cosine of 1 over x. As this goes to infinity and gets very, very big, this whole fraction is going to approach 0. We're going to approach the cosine of 0. This limit is going to be 1. Here, the limit as x approaches infinity of e to the negative x to the third power. This is e over 1. We're going to flip the fraction and change the sign on the exponent. Then we're going to use the power rule. We're going to have 1 raised to the x to the third power over e x to the third. 1 raised to any power is 1. This number is going to get very, very large. This whole limit is going to head to 0. Next, we have this limit, and we recognize this might be a big 5 limit hidden in here. We're going to 0. We got 1 minus cosine x. We recognize that. So let's go ahead and multiply top and bottom by x over x. That's going to yield x times 1 minus cosine x in the numerator. And in the denominator, we're going to have the sine of x times x. So we recognize these as two separate big 5 limits. This one goes to 0, and this one goes to 1. Recall the second big 5 that I alluded to, this one, x over a sine of x, we typically see it flipped. But these limits are both included in the big 5. Therefore, we're going to have 1 times 0, and the final answer is going to be 0. Another way to do this is to use the conjugate. So we could take the top and multiply it by 1 plus cosine x, as well as the bottom. On the top, we're going to get 1 minus cosine squared x. The bottom we're going to leave as factors, 1 plus cosine x. This numerator we recognize as sine squared x. Then one of these signs are going to cancel out, and we're going to end up with applying 0 into this limit. On the top we're going to get 0, on the bottom we're going to get 1 plus 1, 0 over 2 is 0, so we get the same answer. For this limit, first thing we notice is that x is going towards 2. So if we want to use a big 5 limit here, x is supposed to be going to 0. But we see that these are similar. So the first thing I would do here is I would factor the denominator, and we have 5 times x minus 2. So is there an x minus 2 hidden in here? I think there is. So let's pull out a negative 3 and see if that, when we redistribute, we get negative 3x plus 6, negative 3x plus 6. So folks, what we're going to do here is we're going to convert to theta. So we're going to let theta equal x minus 2. And as x approaches 2, then theta is going to approach 0. So we're going to set our limit up as theta going to 0. Now we're going to replace x minus 2 with theta. So we're going to have sine negative 3 theta over 5 theta. Now what we want on the bottom is negative 3 theta. So how do we create that? We multiply top and bottom by negative 3. Now we're going to simply rearrange these factors in different ways. So we're going to have negative 3 out front, a 5 out front on the bottom, and then the numerator becomes negative 3 theta over negative 3 theta. This, with theta going to 0, is a big 5 limit. So this goes to 1, and our final answer is negative 3 over 5. For this limit, we're going to try to invoke the big 5 limit with x going to 0 of sine of the argument over the argument, or the argument over the sine of the argument going to 1. So let's first convert tangent to sines and cosines. So on the top we're going to have sine of 7x, and then the tangent is normally sine over cosine. That's going to become cosine over sine. So we're going to have cosine 2x over sine of 2x. Okay, now here's what we need. And here in pink is how we're going to compensate. Okay, so looking at this first sine of 7x, we need a 7x in the denominator. So we're going to compensate by putting 7x in the numerator. Next, for cosine of 2x, we're going to leave that alone. Cosine of 0 is our friend. That equals 1. But here, when we have sine of 2x in the denominator, we need 2x up here. So we're going to compensate by putting 2x down here. So just to review, we multiplied by 7x over 7x, which is 1, and 2x over 2x is 1. Okay, now if we group these, we're going to have this, the sine of 7x over its argument, that's going to be 1. We're going to have 2x over the sine of 2x, that's going to be 1. These x's are going to cancel out, and we're going to end up with cosine of 2x times 7 over 2, and as x approaches 0, cosine of 2x approaches cosine of 0, which is 1. Therefore, folks, our final limit is 7 over 2. So for this limit, the first thing we're tempted to do is bring the x in the denominator as 1 over x. If we try to use L'Hopital's here, we can't, because the sine of 1 over x as x heads towards 0 means we're taking the sine of infinity, and that does not exist because the sine value fluctuates. But in this case, we recognize that this appears to be one of the big 5 limits, where the argument of the sine function matches what we have in the denominator, and as x goes to 0, you're tempted to say this goes to 1. However, this is one of the big 5 fraudsters, because 1 is not the answer to this limit. And the hint is that your x is in the denominator. So the way we're going to handle this limit is we're going to let u equal the argument 1 over x. Then we're going to rewrite the limit in terms of u. Now we need to figure out what happens to u as x goes to 0. As x goes to 0, as x gets very, very small, u is going to head towards infinity. So right away we know that this is one of the big 5 fraudsters, because when we let u equal the argument and we determine what happens to u as x goes to 0, we get a different answer. Originally x was heading towards 0, now we have u heading towards infinity. So now we're going to change this to the sine of u over u, and this is another big 5 limit that heads to 0. So the final answer to this is 0. Now compare and contrast this to a big 5 limit that we know works. Here, x is in the numerator, and if we were to let u equal the argument and rewrite this limit in terms of u, and we figure out what happens to u as x goes to 0, we see that u also goes to 0. So the fact that the u heads to 0, just like the x did, means we could treat this big 5 limit and trust it, and that limit would be 1. Let's go back to this one up here that we just did. Again, the final answer was 0, but let's use a different technique known as the squeeze theorem. So we're going to restore the limit to its original appearance, original form, and we're going to say that the sine of 1 over x, the sine of any argument, is going to fluctuate between positive 1 and negative 1. Now, to recreate this limit, we're going to go ahead and multiply everything through by x. So this is going to be negative x is less than or equal to x. Sine 1 over x is less than or equal to positive x. Now if we insert 0 here, we're going to have 0 is less than or equal to sine 1 over x is less than or equal to 0. So the fact that this limit, our limit, is being squeezed between these two zeros means the only possible answer is 0. So for this limit, as x approaches 0, we have this product. So we're tempted to put the x squared in the denominator as its reciprocal. And we see that the argument does not match the denominator. So we can't think about using one of the big 5 limits. Also, if we think about trying to use L'Hopital's, which is another reason to create a fraction out of a product, a division problem out of a original product, if we try to use L'Hopital's, we can't here because we're not going to have a L'Hopital friendly situation. Let's look at this limit as x approaches 0. It turns out it's not going to exist. Let's make these numbers a little bit more manageable. I'm going to change this to cosine of 22 over x to the 21. So if we look at this as x approaches 0, and we think about x approaching 0, from either side, whether it's from the right or the left, we're going to be getting very small fractions here, like 1 millionth or 1/100,000th to the 21st power. So if we do look at this, the intuition of this, and this is going to become very, very small, but when we flip it and do keep change flip, this is going to head towards infinity. And we know the cosine of infinity does not exist because it oscillates between 1 and -1. So without L'Hopital's, without using a big 5, let's try the squeeze theorem again. So we're going to originally start with this limit here, which we know, we just reviewed that's going to head, that's going to be between +1 and -1. Okay, so if we multiply through by x squared, this becomes negative x squared this becomes positive x squared. And now we have x squared here, so that is indeed our limit. Now when we plug in 0, again, we're going to have 0 between our limit, 0, then we have our limit, and then 0 again. So our limit is going to go to 0. For this limit, we're going to try to get one of the big 5 in. And we're going to ask ourselves, what do we need and what do we have? Okay, so this is where we're going to put what we need. And actually, not what we need and what we have. What we need, and then how to compensate to make any addition that we insert legal. Okay, so we see we have sine of 5x in the numerator. That means we would love to have 5x in the denominator. So let's compensate by putting 5x in the numerator. With 4x on the bottom, we would love to have 4x on the top. So let's do the same thing, put it on the bottom. So I think that does it. Okay, so let's identify our any big 5 limit. Here's one right there. That gives us a 1. Here's another one. That gives us a 1. And here's what we have left. The x's cancel out, the 4's cancel out, and we're left with 5. So this limit is going to go to 5. So with this limit, if we try to plug in 0, remember, cosine of 0 is nothing to be afraid of. It's only 1. We're going to get 2 times 1, which is 2, minus 5. So we're going to have a negative number within a positive radical, an even radical. So this limit does not exist. With this one, we're going to infinity. We have 2 radicals. Now, you could argue that this one is always going to be bigger than this one. So we're always going to have small minus big. Small minus big. And that we're going to head to negative infinity. But unfortunately, you can't do that. You have to consider infinity minus infinity as indeterminate, and you have to move forward. So what we'll do in this case, we see radicals, we think conjugate. So we're going to multiply by the conjugate on top and bottom. And I went ahead and did the math ahead of time. You could do this on your own if you'd like. And you'll end up with negative 3 divided by the positive version of the original expression. This denominator is always going to be positive because you're always going to get a positive number from these radicals as x approaches infinity. Very, very big number here. Think of a million. You can have negative 3 over a million. That's the same thing as negative 1 millionth. And it's going to just get closer and closer to 0. So this final limit is 0. Next, we have the limit as x approaches 1 of the inverse sine of this rational function. Now, folks, in this scenario, we are going to bring the limit inside. In other words, we're going to take the inverse sine of whatever this limit turns out to be. And we're allowed to do that if and only if this function is continuous as x approaches 1. So we're going to have this. Okay, now, the inverse sine graph, recall, the sine graph, when you talk about inverse sine graph, you only look between negative pi over 2 and pi over 2. So let's look at the sine graph between negative pi over 2 and pi over 2. So we know the sine graph goes from 0 to 1 at pi over 2. And we know it comes down to negative 1 at negative pi over 2. So if this is our sine graph here during this region right there, the inverse sine graph is going to be a reflection over that. Okay, that's going to be 1, and this is negative 1. So the inverse sine is going to be a reflection over that, over the line y equals x. So it's going to look something like this. So it is continuous in this region as x approaches 1. Okay, now that we've done that, we have to figure out what to do here. And you're tempted to use the conjugate, and we could do that. We can multiply top and bottom by 1 over square root of x. But there's a neater way to do this, a more elegant way to do this, and that's to recognize that this here in the denominator is the difference between two perfect squares, because this can be rewritten as 1 plus square root of x, 1 minus square root of x. In other words, x is a perfect square. So if you were to go ahead and FOIL that out, you would get that as the denominator. So let's rewrite the numerator. Now we're allowed to cancel these, and we have an expression that we can plug 1 into. So now, folks, we have inverse sine of 1 over 1 plus square root of 1, so the denominator becomes 2. So the inverse sine of 1/2, excuse me, this should be like this. The inverse sine of 1/2, which is what that limit results in, is going to be pi over 6. Recall, if you look at the unit circle and you use short, medium, and long, if you use short for the sine value, that's going to be the y-coordinate. That angle right there is pi over 6. So the final answer to this complicated problem is pi over 6. Let's take a deeper dive in moving the limit inside. So here we were presented with this limit, the limit as x approaches 1 of the inverse sine of this rational function. So in its original form, we have the limit as x approaches 1 of f of g of x. F is inverse sine, g of x is the rational function. So what we ended up doing is moving the limit inside, and we took the limit of g of x, and when we got that limit, we took f of that. Now, I mentioned a bit about the continuity of the inverse sine, but let's look at that in more detail. First of all, folks, this limit has to exist. So in this case, when we took the limit as x approaches 1, and we took this and we did some algebraic manipulation, we indeed got a definitive limit of 1/2. Now, if we look at the inverse sine, remember the limit is the y value. So if we look at the limit of the inverse sine, if we look at the inverse sine graph when y equals 1/2, it has to be continuous. So let's bring that up. Here's Desmos, and we have y equals sine of x in red and inverse sine of x in blue. So let's look at inverse sine of x, and let's look where the y value is 1/2 and determine, is it continuous? Okay, let's see if I can blow this up a little bit. Yes. Okay, so here's our y value of 1/2 right there, and if we go to the blue, let's get rid of the sine graph. If we go to the blue inverse sine graph, we could see that when y equals 1/2, it is continuous. And if we look at what the x value is, it's going to be pi over 6, which is 1/3 the distance from 0 to pi over 2. So when you're given a situation and you're trying to decide, should we move the limit inside, the first thing you have to do is make sure that the limit exists. Once you find that a definitive limit exists, then you determine, is the outer function f continuous at that y value? So when we originally plugged in, we got 0 over 0, but we were allowed to do algebraic manipulation to get a definitive limit. Next, we are given the limit as x approaches 1 of the inverse tangent of this rational function. And if we were to plug in directly, we would get 2 over 0. Now here, folks, if we want to consider moving the limit inside, we have to make sure that the limit exists. So let's go ahead and see if the limit as x approaches 1 of 2 over x minus 1 exists. And here, we cannot do any algebraic manipulation. There's nothing to factor and cancel. These are not difference between two perfect squares. Can't do long division, etc. So in a circumstance like this, we have to evaluate the limit approaching 1 from both sides. So there's two ways to do this. We could do this graphically. We recognize how to graph this rational function. We see that it's bottom heavy, which means it's going to have a horizontal asymptote at y equals 0. We see that it's going to have a vertical asymptote at x equals positive 1. And because this is to the first power, these asymptotes are going to go in different direction, meaning one is going to head towards positive infinity, one's going to head towards negative infinity. And in order to determine which is which, you would do a sign analysis of all the critical points. So to do a sign analysis of the critical points, we look at the zeros and the vertical asymptotes. There are no zeros, so the only sign analysis critical point is positive 1. So if we're in zone 1, we are going to plug in a test point over here, which would be 0. If we plug in 0, we see that we get a negative value. So that means our graph is going to be negative to the left of 1. And if we put in a test point of 10 here, we're going to see this is going to be 2 over 9, which is positive. So folks, this is our graph. And if we want to get our y-intercept, we can plug in 0 by putting our thumb over the x, and we're going to get negative 2. So this is our graph right here. And we could see that as x approaches 1 from the left, we're going towards negative infinity. As x approaches 1 from the right, we're going to positive infinity. Therefore, this limit does not exist, and therefore we are not allowed to bring this limit in. Okay, so how do we approach this limit? And folks, before I get there, let's talk about what to do if you didn't know how to graph that rational function for whatever reason. Okay, what we would do is we would have to approach this limit from both sides. So let's first look at the limit as x approaches 1 from the left of 2 divided by x minus 1. Let's look at the number line. And we see if we're approaching 1 from the left, first we might plug in a number, let's say 0.9 for x. Okay, so if we plug in 0.9 for x, we're going to have on the bottom 2 divided by 0.9 minus 1. Okay, when the signs are different and you're doing subtraction, you do big minus the small, and then you take the sign of the larger number. So here, the big is the 1, the small is the 0.9. If we do big minus small, we're going to get 0.1, and we're going to use the negative because the 1 is bigger. So as we approach 1 from the left, if the first number we put in is 0.9, this is going to evaluate in the denominator to negative 0.1, otherwise known as negative 1/10. So let's put negative 1/10 in the denominator. And if we multiply both sides, top and bottom, by 10, we see that this becomes negative 20. Okay, now look what happens, folks, when we put in a number closer to 1. Let's put in 0.999 and see where that takes us. Okay, so now we're going to put 0.999. So again, we're going to do 0.999 minus 1. And when we do that, we're going to do big minus small. So it's going to be 0.999 minus 1. So that means we're going to do 1.00 minus 0.999. And here, folks, we're going to get 0.001. It's going to take the negative sign because, again, big minus small, and you take the sign of the big number. Now what we have is negative 0.001 in the denominator. That is negative 1 over 1,000. Okay, now if you multiply both sides by top and bottom by 1,000, we're going to get negative 2,000. So you could see we went from negative 20 to negative 2,000 as we're approaching 1 from the left. That means this limit is heading towards negative infinity, just like our graph predicted. Okay, now if you do it the other way, you will find that you're going to be getting larger and larger positive numbers as you approach from the right. And for example, let's just do one of those very quickly. So if we're approaching from the right, our number line now is going to have, say, 1.001. Now when we do big minus small, we're going to take the sign of the larger number. When we do big minus small, we get 0.001, but that's positive, 0.001 positive. So now when we have 2 over 0.001, that's 2 over 1,000th. And now when we multiply top and bottom by 1,000, we're going to get a big positive number, positive 2,000. So if you don't know how to do the graph, that's how you approach this. Okay, so we know that that limit does not exist. Therefore, we cannot bring this limit inside and do it like we did the previous problem. So let's talk about how to approach this limit. And the answer is we're just going to have to do it from both sides and take the inverse tangent of negative and positive infinity. So let's go ahead and do that. So the limit as x approaches 1 from the left, we already know that this is going to be the inverse tangent of negative infinity. So if we look at our unit circle, we see that the tangent, which is otherwise known as the slope, is going to be negative infinity right there when x equals negative pi over 2. And then if we do the inverse tangent, the limit as x approaches 1 from the right, that means we're going to be taking the inverse tangent of positive infinity. And where is the tangent positive infinity? None other than pi over 2. And if the fact that these are not the same means this original limit does not exist. Recall, if this unit circle doesn't help you figure out the tangent, recall the graph of the tangent function. It's centered about the origin. It's an increasing function. First asymptote at negative pi over 2, second asymptote pi over 2, and you could see that the limit, or the inverse tangent of x equals pi over 2 is going to be a y value approaching infinity, and similarly approaching negative pi over 2, our y value is going to be negative infinity. So this original limit does not exist. We have the limit as x approaches infinity of the natural log of this rational function. So the question is, can we bring the limit inside? We can only if this limit exists. So if we look at this rational function, we see it's bottom heavy. So as x approaches infinity, this is going to approach 0. So the limit does exist. So we could bring the limit inside. So now what we're thinking is, as x approaches infinity, that argument for the log is going to approach 0. And as the log argument approaches 0, the natural log of that is going to be negative infinity. Very important, folks, to know all of your graphs. That's the graph y equals ln of x. as x approaches 0, you could see that y is approaching negative infinity. Folks, I want to make a small addendum to that last limit. Namely, I want to make sure that we're on the same page in terms of the fact that as x approaches infinity, this rational function is going to approach 0 from the positive side. And the reason is if it was a possibility that it approached 0 from the negative side as well, then the limit would not exist. But this limit is only going to approach 0. This rational function is only going to approach 0 from the positive direction. And the reason is this fraction is always going to be positive, because you're only going to have positive inputs as this limit progresses. So 2 times x to the cubed is going to be positive, x to the 5th is going to be positive, the 9 and the 12 are going to be insignificant. So this is going to be positive and bottom heavy. This rational function itself is going to have a horizontal asymptote that's going to head towards 0 from above, and all the values are going to be positive. Therefore, we could safely say that x is going to approach 0 from the right, and therefore the y value, namely the limit, is going to approach negative infinity. I want to say a few words about the importance of understanding the difference between dealing with a log and dealing with an integer. Up top, we're going to use the power rule, and because this is just an integer, we're going to have 4 to the 6th power. Here, 2 to the ln of x, entire function raised to the x, because this is an x, because that 2 is an integer, we can legally say this is the same as x times ln x. However, things change when we're dealing with a log function. And these two are different problems. In the pink here, we have the x is modifying the entire log function, whereas here in the orange, the x is only modifying the argument. So this right here would be a little bit more explicit, making it clear that that x only applies to the argument. So here, you are not allowed to call this. This is not allowed. You are not allowed to say this is ln e to the 2x. Incorrect. The way to handle this problem is to evaluate the inside of the parentheses first. So we're going to have ln e squared raised to the x power. Here, these cancel out, and we're going to end up with 2 to the x. Over here, we're going to have ln of e, and the argument is now going to be e to the 2x, and this cancels out, and your final answer is 2x. Next, we have the limit as x goes to infinity, log base 2 with an argument of x plus 2 over log with a base 3 of an argument x plus 1. So if we plug in infinity to both of these, we're going to get infinity over infinity, so that is L'Hopital's friendly. So we're going to take the derivative of the top. When we take the derivative of a log function, it's 1 over the argument times the derivative of the argument, which in this case is 1, times 1 over natural log of the base. Okay, we're going to do the same thing on the bottom. 1 over the argument times the derivative of the argument times 1 over the natural log of the base. So therefore on the top we're going to have 1 over x plus 2 times ln of 2 over 1 over x plus 1 times ln of 3. Okay, next we're going to do keep, change, flip. We're going to keep this exactly as it is, and we're going to flip the denominator. So this becomes x plus 1 times ln 3 up top. Okay. Next, we're going to distribute both top and bottom. We're going to distribute backwards, and we're going to end up with, here in red, x ln 3 plus ln 3 over x ln 2 plus 2 ln 2. Okay, folks, don't forget, we're applying the limit to this as x goes to infinity. Okay, at this point, there's two ways to approach this. First, you could just use the intuition that when x is going to infinity, only the x terms are relevant. Therefore, we could just ignore these two, because these are constants, and divide the two x's, and we end up with ln over 3 divided by ln over 2, which is indeed the final answer. If you don't not a fan of using the intuition, the other thing you can do is come along and divide all the terms by the highest x degree that's in the denominator. So therefore, if we make some room here, if we divide everything by x, remember, as x goes to infinity, these terms are going to go to 0. So now we can cross out the x's, and we get the same answer of ln of 3 divided by ln 2. Next, we have the limit as x approaches 0 from the right of this function x to the x. Folks, I did a separate video on this, on how to take the derivative of that function. And during the video, we talk about the fact that you can't treat this as 2 to the x, or you can't treat this as x squared. Meaning, when you take the derivative, you cannot use the power rule here because this is not a constant. And you can't take the derivative as if this was an exponential function because the base is not a constant. But during that video, we talk about how to change this x as follows. We're going to change x to e to the ln of x. And we're allowed to do that because recall that the base of the natural log is e, and when the base here matches the base of the log, we're allowed to cancel everything and you're left with the argument. So we're going to rewrite this as the limit as x approaches 0 from the right of e to the natural log of x raised to that original blue x. And when we're in this situation, we can execute the power rule there of exponential functions, and therefore we're left with the limit as x approaches 0 from the right of e to x times natural log of x. Okay, so folks, let's do some erasing here, and what we're going to do now is we're going to bring the limit into the function, and we can only do that if the limit exists. In other words, we're going to take this limit and we're going to bring it in. So now we're going to look at the limit as x approaches 0 from the right of x times ln of x. Okay, here we would get 0 times negative infinity, which is indeterminate. When it's indeterminate, it means we need to do more work. So what we're going to do is we're going to create a fraction in hopes that L'Hopital's rule is usable. So we're going to take that x, we're going to bring it down below and change it to 1 over x. Now we're going to place 0 in here. We're going to get negative infinity on top, positive infinity on the bottom. This is L'Hopital's friendly. We're now going to go ahead and take the derivative of the top and the bottom. So the derivative of natural log of x is going to be 1 over x in the numerator. And in the denominator, we're going to change that to x to the minus 1 and use the power rule. And we're going to end up with negative x to the negative 2 power. I'm going to change the numerator to x to the minus 1. And then I'm going to take this x to the minus 2 and bring it up top and change the sign of the exponent. That negative 1 stays down below. You cannot move that negative up and make it a positive. So now, moving this way, if we multiply, we're going to keep the base and add the exponents. So we're going to end up with x to the first power over negative 1, or negative x. Now, when we apply the limit, when we plug in 0 here, we're going to get negative 0, otherwise known as 0. So now, folks, we're going to have e to the 0, otherwise known as 1. So 1 is your final answer on this complicated limit. Next, we have the limit as x approaches 0 from the right of x raised to the 1 over 1 plus ln of x. So folks, we're going to use the technique where we change x to a version of e. So we're going to change this to the limit as x approaches 0 from the right of e to the ln of x. That replaces x raised to the original exponent, 1 over 1 plus ln of x. Then we're going to go ahead and use the properties of exponents. Power rule, power raised to another power allows us to multiply these two. So now we're going to have the limit as x approaches 0 from the right of e to the ln of x over 1 plus ln x. Okay, folks, we're going to move the limit inside, and we're going to get e to the limit as x approaches 0 from the right of ln of x over 1 plus ln of x. Now, folks, we're going to go ahead and do this limit. Okay, to do that, if we plug in 0 plus, we're going to have negative infinity over negative infinity. Therefore, that is L'Hopital's friendly. We're going to take the derivative of the numerator and the denominator. In the numerator, we're going to get 1 over x. In the denominator, the derivative of 1 is 0. We're going to get 1 over x again. So this is going to become just 1. So if that's the limit, after we apply L'Hopital's rule, we're going to get e to the first power, otherwise known as e. We have the limit as x approaches 0 of x times e to the x divided by e to the x minus 1. If we attempt to plug in 0, we have 0 times e to the 0, or 1, which is 0 on top. And on the bottom, we're going to have 1 minus 1, so this looks to be L'Hopital's friendly. On the top, we're going to take the derivative using the product rule. Left times the derivative of the right plus right times the derivative of the left. On the bottom, the derivative of e to the x is e to the x, and the derivative of the constant negative 1 is 0. On top, we're going to pull out e to the x as a greatest common factor. The e to the x's cancel out, and now we're able to plug in 0. Our final limit is 1. Next, we have the limit shown here, and folks, the idea here is to try to get a fraction and hope that it is L'Hopital's friendly. So we're going to have a common denominator. We're going to multiply the two denominators to get it. This first term, the ln of x, is missing, so we're going to multiply ln of x over ln of x, and we're going to have x ln of x. Here in the second term, the x minus 1 is missing, so we're going to multiply x minus 1 over x minus 1, and we're going to end up with x minus 1 up top. Next, we're going to distribute that negative to get x ln of x minus x plus 1 over x minus 1 times ln of x. Okay, if we try to insert 1 here, the natural log of 1 is 0. Excuse me. So this is going to go to 0, and then we're going to insert the 1 for x. Minus 1 plus 1 is 0. 0 over 0, that is indeed L'Hopital's friendly. So we're going to go ahead and take the derivative of the top and the bottom. On the top, we're going to use the product rule for the first term. Left times the derivative of the right plus the right times the derivative of the left. The derivative of x is 1, and derivative of 1 is 0. On the bottom, I think it'll be a little bit easier if we distribute first. So let's distribute, and we're going to have x, ln of x minus ln of x. So if we take the derivative of that, first we're going to get exactly what we had on the top to start. And then we're going to have minus 1 over x. Okay, so we can cross these out, and we're going to end up with natural log of x up top, because 1 minus 1 is 0. On the bottom, we're going to have 1 plus ln of x minus 1 over x. Okay, can't really do much with this, folks. We're going to insert 1 in here again, and when we do, we're going to get 0 over 0 again. So we're going to go ahead and apply L'Hopital's rule again. Let me make some room. Okay. We take the derivative of the top, we're going to have 1 over x. On the bottom, derivative of that is 0. Derivative of ln of x is 1 over x. Now I'm going to change this to minus x to the minus 1, and I'm going to do the power rule. So that's going to end up being plus x to the minus 2. Okay, so now if we try to insert 1 here, we're going to have 1 over 1, which is 1, 1 over 1, which is 1, plus 1 to the negative second power. 1 to any power, folks, is 1. So even if we have 1 to the minus second power, that's going to be 1 over 1 squared. We're still going to get 1. So our final limit here is going to be 1/2. So here's an instance where we had to use L'Hopital's twice. We have the limit as x approaches 2 of x squared minus 4 over natural log of x minus natural log of 2. So folks, if we plugged in 2 here, we're going to get 0 over 0, and that qualifies to use L'Hopital's rule. So we're going to take the derivative. Now we're not going to use the quotient rule. We're just going to take the derivative of the numerator and take the derivative of the denominator. So in the numerator, we're going to use the power rule. In the denominator, we need to review the natural log of x derivative. So here's a general form of how to handle logs. If you have log base a with the argument u, it's 1 over the argument times the derivative of the argument, so think of that as the chain rule here, times 1 over the natural log of the base. So in this case, if we have natural log of x, of course that's to the base e. We're going to have 1 over the argument times the derivative with respect to x of the argument. The derivative of x is just 1, times 1 over the natural log of the base, which is e. So recall, when you take the natural log of e, The base is e, the argument is e. If the base of the log matches the base of the argument, they cancel out and you're left with the exponent. So when all the smoke clears, you have 1 over x times 1 over 1, otherwise known as 1 over x. Okay, so the natural log of x is just going to be 1 over x, and the natural log of 2 is going to be 0, because that's a constant. Remember, folks, the ln of x graph looks like this. So ln of 2 is going to be some constant value. When you take the derivative of a constant value, you get 0. Okay, we're left with this complex fraction here. We're going to multiply the top and bottom by x, and we're going to end up with 2x squared in the numerator. When we plug in 2 here, we're going to have 2 times 2 squared. Because of PEMDAS, we're going to do that first. 2 times 4 equals 8. And that is your final answer of the limit. Next, we have the limit as x approaches 0 of 1 over x minus 1 over the inverse tangent of x. So if we try to plug in 0 here, we end up getting, we have a finite number in the numerator over 0, so we can call that infinity. And again, the inverse tangent of 0 is 0. Recall that if you have the unit circle and you have inverse tangent of 0, that is going to be 0 degrees, because the tangent of that 0 degree angle is in fact a horizontal line. Therefore, the slope equals 0. So we have an infinity minus infinity situation here. It's indeterminate. So the idea here, folks, is to create a fraction, because if you get a fraction, then you might get lucky and have it qualify for L'Hopital's rule. So what we're going to do is we're going to create a common denominator, and that common denominator is going to be these two denominators multiplied by each other. And then we're going to multiply each separate term by a version of 1 that allows us to get the common denominator. So 1 over x is missing the inverse tangent x, so we're going to multiply by inverse tangent of x over inverse tangent of x, which is a version of 1, totally legal. Here, this term lacks the x, so we're going to multiply by x over x. And when we do all of the above, and then we add the fractions, we end up with this expression right here. Now, folks, if we plug in 0 for x, on the top we're going to get 0 minus 0, and on the bottom we're going to get 0 times 0. In summary, we're going to get 0 over 0, and this is L'Hopital friendly. So we're going to take the derivative of the top and the bottom. We're not going to use the quotient rule. So when we look at the derivatives of inverse trigonometric functions, they're listed here. And the good news is that we don't have to memorize all of them, because if you notice, the cofunctions they differ only by a minus sign. So the cosine and the sine differ only by that minus sign, similar for the tangent and its cofunction, cotangent, and secant and its cofunction. So really, folks, you only need to memorize these three, in my opinion: the sine, the tangent, and the secant. So we're interested in the inverse tangent. The way I remember it, that this is inverse tangent, is it's the only one of the three that lacks a radical in the denominator. So I envision removing that radical similar to removing an umbrella that's blocking the sun, and when you do that, you get tanned. So that's how I remember that the derivative of the inverse tangent function is 1 over 1 plus x squared. Okay, so when we apply that derivative, so we're basically applying the d dx operator to the numerator and the denominator. So as we just saw, the derivative of the inverse tangent of x is 1 over 1 plus x squared. and the derivative of x is just 1. On the bottom, we do have to do the product rule. So this times the derivative of that is going to be x times 1 over 1 plus x squared. And then this times the derivative of that with an addition sign in the middle, and we're going to have inverse tangent of x. Okay, folks, you have a couple of options here. We could go ahead and see what happens now that we apply the limit to this function. And when we do that, we see that if we put 0 for x squared, that's going to go away. 0 for x squared, 0 for x, and the inverse tangent of x is also going to be 0. So we're going to end up with 1 minus 1 on the top and 0 plus 0 on the bottom. So again, we have 0 over 0. So now, folks, we have two options here when we look at performing the derivative of the numerator and denominator once again. We could go ahead and simplify this and get rid of these complex fractions. To do that, we would multiply by 1 plus x squared on the top and the bottom. So that's one option. Or you could take the derivative as is and simply use the quotient rule here. So folks, I'm not going to torture you with redoing the derivative and plugging in 0, because this is a video on limits, what to do. But the bottom line is you would want to go ahead and take the derivative of this function by either combining the complex fractions or going ahead and using the quotient rule. And when you do all that and you plug in 0, the bottom line is you're going to get 0 over 2. So the answer to this limit is 0. Next, we have the limit as x approaches 0 from the right of x times ln of x. So if we try to plug in 0 directly, we're going to get 0 times negative infinity. Recall that the graph of ln of x looks like this. So as you approach 0 from the right, the y value is going to head towards negative infinity. Well, this, of course, is indeterminate, so we have to do some algebraic manipulation. So when you're in a circumstance like this, the idea is to try to create a fraction. Because if you have a fraction, you might be able to use L'Hopital's. So what we're going to do, folks, is we're going to change this to ln of x divided by 1 over x. Now, if we go to plug in 0, we're going to have negative infinity over positive infinity, and that is L'Hopital's friendly. So now we're able to take the derivative. We're going to take the derivative of top and bottom. We're going to apply the ddx operator. The derivative of natural log of x is 1 over x. And to take the derivative of this, I'm going to change this to x to the minus 1. So when we do the power rule, we're going to bring the negative 1 out front, and we're going to get negative x to the minus 2. Okay, then to simplify this, we're going to change the numerator to x to the negative 1. And then we're going to bring this x to the negative 2 up to the numerator and change that to x to the positive 2. And we have that negative 1 underneath. Recall, when you bring a base and its exponent up or down, you change the sign of the exponent only. The negative 1 coefficient stays where it was originally. So now we're multiplying, the bases are the same, we keep the base and we add the exponents, and we have negative x to the first power. Now if you plug in 0, the limit ends up being 0. Next we have the limit as x approaches 0 from the right of x times e to the 1 over x. So if we plug in, we're going to have 0 times infinity, which is indeterminate. So what we want to do is create a fraction. So we're going to have the limit as x approaches 0 from the right of e to the 1 over x over 1 over x. Now if you plug in 0, we're going to have infinity on top and infinity on the bottom. That is L'Hopital's friendly. So we're going to take the derivative of both the top and the bottom. Derivative of e to anything is you just rewrite it. Then we're going to take the derivative of the exponent. If you think of this as x to the minus 1, we're going to have a negative out front and becomes x to the negative 2. And finally, we do ln of the base. Ln of e is just 1. On the bottom, we're going to have x to the minus 2, negative x to the minus 2 for the same reason that we did on the top. We see that these conveniently cancel out, the negatives cancel out, and we're left with the limit as x approaches 0 from the right of e to the 1 over x. Folks, if you have a very, very small positive number here, this is going to end up being e to the infinity, which is just infinity. Recall the graph of e to the x looks like so. So this is y equals e to the x. So if you plug in a very, very large number for x, you could see the y value heads towards infinity. For the limit shown here, if we plug in infinity for x, we're going to have infinity. And looking in the parentheses, we're going to have 2 to the 1 over infinity. 2 to the 1 over infinity minus 1. 2 to the 1 over infinity is the same as 2 to the 0 power, because that goes to 0, minus 1. And 2 to the 0 power is 1. 1 minus 1 is 0. So this is infinity times 0, indeterminate. Can't do anything with it. The idea is to create a fraction. So let's go ahead and do that. You've seen that a few times before. We're going to bring the x down below and change that to x to the minus 1, otherwise known as 1 over x. Now if we go ahead and plug in, we know we're going to get 0 on the top, and on the bottom, if we plug in infinity down here, that goes to 0. We now have 0 over 0, which is indeed L'Hopital friendly. So let's change this to x to the minus 1. Take the derivative of the top and bottom. Apply the ddx operator. Okay, so the derivative of this, we're going to rewrite 2 to the 1 over x. Then we're going to take the derivative of 1 over x. We know that to be negative x to the negative 2. And then we have to take the natural log of the base. And on the bottom, we're going to get negative x to the minus 2. Okay, folks, this is going to cancel out. This is going to cancel out. So now we have 2 to the 1 over x times ln of 2, the limit as x approaches infinity. Again, if this approaches infinity, this whole fraction goes to 0. So we're going to have 2 to the 0 times ln of 2. 2 to the 0 is 1. Our final answer for this limit is ln of 2. Next, we have the limit as x approaches negative infinity of 3x divided by the square root of 4x squared plus 9. So folks, the fact that our domain is going to involve inputs of negative values immediately alerts us that we might be inserting a negative outside this radical. And I refer you to the entire separate video on my site that discusses the intuition as to why this is so. But here, like with any rational function, we're going to divide top and bottom by the highest degree in the denominator. Now, it's the highest degree in the denominator is not x squared because that's inside the radical. So rather, we're going to be dividing by x to the first, which is the same thing as multiplying by 1 over x to the first. So on the top, the x's are going to cancel out, and we're going to have 3 in the numerator. Now on the bottom, we're going to get set up we're going to create a fraction here inside the radical in anticipation of inserting that x to the first into the radicand. And when we do that, exponents get bigger. Going in the radicand results in a bigger exponent. So we're going to be inserting x squared in here underneath that fraction line. Now, folks, very important, the fact that this is an odd exponent entering an even radical and we have negative inputs mandates that we insert a negative in front of this whole denominator. Okay, so let's rewrite this. Now we're going to have this now 1 over x to the first is now going to disappear from the outside of the radical and end up in the radicand. So we have two separate terms. I'm going to divide each term separately by the x squared, and we cannot forget that all-important negative that we inserted due to the fact we have an odd exponent being inserted into an even radical. This is going to go to 4 on the inside. That's going to go to 0. As that goes to negative infinity, this term goes to 0. Folks, that's going to give us 3 over minus square root of 4. Our final answer is going to be negative 3 over 2. Next, we have this limit, and we're going to do it both going with x going to infinity and the limit as x goes to negative infinity. Okay, so we see the radical there. We're going to divide top and bottom by the highest degree in the denominator. So we're going to divide by x squared on the bottom, and on the top we're going to multiply by 1 over x squared, and we're going to insert this into the radical. Now, of note, this is an even radical. This is an even power that's going into the radical. So we do not need to worry about inserting an extra negative out here, even if we're going to negative infinity. If you have an even root, an even exponent going into an even root, no need to worry about adding that extra negative sign. Okay, now don't forget, when we insert the x squared into the radical, when we go in, we get bigger. So x squared is going to go in as x squared squared, or x to the fourth. Okay, so on the top, we're going to have the square root of 5x squared over x to the fourth plus 3 over x to the fourth. Okay, on the bottom, we're going to have the following. Because we insert infinity here, these are going to cancel out. We're going to have 7, but infinity in the denominator, big denominator, big denominator. These are both bottom heavy. They both go to 0. Okay, so what's happening up top? Up top, that's going to go to 0, and here this first term is going to go to 0. So we're going to end up with 0 over 7 for a final limit of 0. Folks, the same exact thing is going to happen here. We don't need to do this problem because, again, we are not inserting a negative in front of that radical. And the same thing happens when you insert negative infinity. It has the same effect as blowing up the whole fraction to 0. Let's now do these two limits, both going to infinity and negative infinity. So again, we have radical. We're going to divide top and bottom by the highest degree in the denominator. So that is tantamount to multiplying the top by 1 over x. Now we're going to go ahead and rewrite this radical with fractions in anticipation of inserting this x to the first into the radical's denominator. Now, the fact that this is an odd exponent going into an even radical, we have to be mindful of whether or not we have any inputs that are negative. Since this is going towards positive infinity, we do not. However, if you take a peek down below, for sure, because that's a negative, heading towards negative infinity with negative inputs, if you're taking an odd exponent, inserting into a even radical, we're going to be adding an extra negative. I'm going to go ahead and do it right now before I forget. Okay, moving on here, if we write our three terms, 3x squared minus 7x plus 2, don't forget that x first on the outside gets squared. When you go in, you get bigger, and it becomes x squared inside the radical. In the denominator, we're going to have 2x divided by x plus 7 over x. Okay. Here in the radical, x squareds are going to cancel out. That's going to go to 0. That's going to go to 0. We're going to have the square root of 3 in the numerator. On the bottom, these are going to cancel out. That's going to go to 0. And our answer is going to be square root of 3 over 2. Folks, on this one, the answer is going to be negative square root of 3 over 2. We're going to do the same thing. Divide top and bottom by x to the first. Insert that as x squared. And the same algebra is going to occur. The only thing that's different is that added negative. So for this limit, this is a two-sided limit. It's a standard limit, and we have an even radical function. So folks, we have to remember that the domain of this even radical is limited. So if we set the radicand equal to 0, we're going to find that x equals 7 is going to be the vertex, 7, 0 specifically. So this function is going to look something like this. Because this is positive and that's positive, it's going to head towards the first quadrant. So if this is x equals 7, we have to remember that yes, as x approaches 7 from the right, this would be 0. However, x approaching 7 from the left can't occur because of the limited domain. So therefore, the limit as x approaches 7 from the left does not exist. The limit as x approaches 7 from the right equals 0, but the definition of a limit is that the limit from both sides have to be equal for it to exist. Therefore, the entire limit does not exist. For this limit approaching 1 from the left, let's go ahead and do a number line, get an intuition of this. So here's positive 1. Approaching from the left, we're going to have numbers that are less than 1. So if you imagine having 0.9 here, this is going to be 3 minus a number smaller than 3, figure 2.9. Still going to be positive, so it's legal under the radical. But as we get closer and closer to 3, this difference is going to get closer and closer to 0. So this limit is 0. Because it's a one-sided limit, we don't have to worry about from the right. For this limit, the first thing we notice is we're heading towards negative infinity, but that's an odd root, so we don't have to worry about inserting any negatives. The unique aspect of this limit is that the radical involves both the numerator and denominator. So let's get the intuition as to what the end behavior is of the radicand. So here, this is a rational function, and the degrees are the same on top and bottom. So therefore, the horizontal asymptote, the end behavior, is going to head towards negative 1. So basically, we have the cubed root of negative 1, which is just going to be negative 1, and that indeed is the answer to this limit.